Glaciers are an absolutely amazing geologic phenomenon. They are familiar to everyone in a vague sense, but their geologic impact and their importance to human beings isn't well known. A glacier is a body of ice, but the geologic definition also includes snow and recrystallized snow from previous seasons, known as firn. The presence of snow and firn in the definition already indicate the importance of snowfall and the time it takes to recrystallize the snow in a process of forming a glacier. A glacier is also defined as having evidence of past or present movement. This is one of the more interesting things about understanding glaciers. They are solid ice, yet they move. Normal flow rates are a couple of feet per day, but the fastest moving glacier, Jakobshavn Glacier, in Greenland was clocked at over 150 feet per day in 2012. Finally, a glacier has to lie entirely or mostly on land. That's the component of the definition that eliminates icebergs. Glaciers, to provide perspective, cover about 10% of the land area of Earth. During the last ice age, which reached a maximum glacial extent about 25,000 years ago, over 30% of the land area of the Earth was covered. Glaciers store about 75% of the world's fresh water, and if all the glaciers on the planet melted, sea level everywhere, which is over 70% of the Earth's surface, would rise over 200 feet. I hasten to add that all the world's glaciers aren't going to melt anytime soon, but it has happened several times in the past, like the Eocene period from 50 to 34 million years ago when there were no glaciers on Earth. That was just before the Antarctic ice sheet began to form. Understanding glacial processes helps us understand a variety of landscapes, and glacial deposits often strongly influence the soil that forms on them. Glacial deposits contain materials of economic value, including sand, gravel, and clay. Glacial processes frequently result in the formation of large wetland areas, and many of the world's economic peat resources have formed in glacial terrains. Melting glaciers provide fresh water, especially during summer months. In montane agricultural regions, summer is the time when the most water is needed, and that's also the time that the mountain glaciers and snowpacks are melting. In Washington State, for example, melting glaciers provide over 400 billion gallons of water each summer. That's important because most of Washington's precipitation, roughly 42 inches per year, occurs during winter months. Additionally, glaciers are closely tied to climatic conditions. Obviously, they are an indicator of cold climatic conditions. As a result, the glacial record provides insight into the changing global climate and the evolution and extinction of organisms that lived during those events. So how does a glacier form? It just gets cold, right? Well, essentially that's true, but there are critical components of it. The first is snowfall. Say, for instance, we're going to generate a glacier. How do we do that? Is it a matter of piling up snowfall upon snowfall? Well, not quite. The critical thing is generating snowfall and not letting that snowfall melt. Once climatic conditions become cold enough, snow will begin lasting through the summer. In the winter, snow piles up on top of the previous year's snow. And again, if it's cold enough, that snow will last through the year. Over time, and with increased pressure caused by the increased thickness of the accumulating snow, buried snow will begin the transition from snow to firn. Generally, it takes weeks and an overburden of 20 feet of compacted snow. In this process, the snowflakes that you envision, those hexagonal, six-fold symmetric crystals, begin to turn into very compact and much more dense ice crystals. With increased time and increased pressure due to overlying snow and firn, the transition to glacial ice occurs. In addition to the generation of denser ice particles, a couple of interesting things happen. One is you start generating glacial ice crystals. With increased pressure, water molecules continue to crystallize just like any mineral. A single glacial ice crystal can grow to the size of a baseball. As crystals are squeezed together, the ice becomes more dense. In fact, it is the density of glacial ice that gives it that spectacular blue color that can be either light blue or dark blue. This is the result of dense glacial ice absorbing every other color of the spectrum except for the blue wavelength, which is reflected. It's really one of the characteristic traits of a glacier. By the way, even ice cubes do reflect blue, but the color is too pale to register with the human eye. The other thing that happens is that air becomes trapped between the ice crystals. Accumulating snowflakes are really porous, so a lot of air is held in layers of snow. With increased pressure, some air is trapped in small pockets. Over time, as ice crystals grow into one another, the ice crystals will trap the air pockets as bubbles. As the glacier thickens, the bubbles are preserved under high pressure conditions. Scientifically, this is incredibly important. Bubbles in glacial ice preserve samples of the atmosphere at the time when the snow fell. Cores of ice sheets provide a continuous record of the Earth's atmospheric conditions that go back 50,000 years. This provides a phenomenal record of changes in the atmosphere. There's also a less profound benefit of bubbles in glacial ice. When you spend time on glaciers, it's fun to throw a piece of glacial ice in a glass of your favorite liquid. As the ice melts, the bubbles trapped in it begin to expand and will literally pop, breaking apart the ice in the process. It makes for a lively drink. Of course, getting a little glacial sediment in your drink is part of the trade-off, so it's not perfect. But when you're in the field, you take what you can get. In order to generate glacial ice, you have to have climatic conditions that are cold enough to enable snow to last through the summer. This means that wherever the snow is accumulating, in the mountains or at a high latitude, the summer temperatures do not exceed 0 degrees Celsius long enough to melt all of the previous winter's snow. So to generate a glacier, you need to have enough land surface where the average annual temperature is below 0 degrees Celsius. If you look at modern glaciers, especially in the late summer, it's easy to identify where the glacier is melting and where the glacier is still accumulating snowfall through the year. The area that's melting near the margin of the glacier is frequently grayer and covered with debris at the end of the summer. In contrast, up ice, you frequently see places where the glacier is nearly pure white and no debris is exposed. What you're seeing is called the equilibrium line. It's the elevation on a glacier where the portion of the glacier that's melting is easily distinguished from the portion of the glacier that's accumulating new snow year after year. If you think about it, the equilibrium line becomes a dividing line for average annual temperature. Above the equilibrium line, the snow that falls doesn't melt, at least not all of it. That means that the average annual temperature above the equilibrium line is colder than 0 degrees. Below that dividing line, any snow that fell during the past winter has melted. What's exposed is old firn or glacial ice. That means that the average annual temperature is warmer than 0 degrees Celsius. This means that over time, watching the equilibrium line, either by using photos, paintings that are historically accurate, or scientific surveys, one can tell whether the elevation of the 0 degree isotherm is changing. You probably won't be surprised to hear that the record of equilibrium lines on glaciers around the world has shown that the 0 degree isotherm is moving to higher elevations. The size of a glacier, the glacier's dimensions, and the position of its edge, or terminus, are related to a number of things. Most importantly, the glacier's budget. Like any budget, you take into account income versus outflow. If you're dealing with a household budget, you want to be taking in more income than you're spending. It makes for a healthy and perhaps happy household. Similarly, when thinking about glaciers, if they are expanding or if the terminus of the glacier is advancing, you think about a glacial budget. If in a given year you receive more snowfall that lasts through that year in comparison to the amount of ice that melts during that year, then the glacier will get larger. If more melting than accumulation occurs, then the glacier will get smaller. This is called mass balance. Glaciologists, people who study glaciers, will monitor the mass of snow, refrozen meltwater, and any other additions to the glacier versus the amount of meltwater produced. Over a long period of time, reduction in mass means the glacier gets smaller and the margin retreats. This is what's happening now in most of the world's glaciers. The glacier in this photo is entirely below the equilibrium line. All of last winter's snow has melted. It is doomed. This is one of those alpine glaciers that will disappear in 30 years. This is, of course, an important observation, but a lot of times the media doesn't focus on equilibrium line. Rather, the media reports tend to focus on the ice margin, also called the edge or the snout of the glacier. The position of the margin of a glacier isn't always directly related to climate. Changes in flow rates or subglacial conditions can also influence the position of an ice margin. But it can be the case that a glacier's terminus advances even in warmer conditions. This is a function of the flow of the glacier. If the flow rate of the glacier increases, then even in warming conditions you can see an advance of the terminus. This makes for interesting television news because the glacier appears to be growing just as temperatures increase. Once enough glacial ice is formed, the glacier begins to flow. The process of glacial flow involves two components. One is internal deformation of the ice mass, and the other important one is basal sliding. Internal deformation is exactly what it sounds like. The ice deforms. Ice is one of those interesting solids that's capable of flow. These solids are called rheads. Glass is another example of a rhead. If you go into an old castle or cathedral in Europe and look closely at the windows, you may see air bubbles in the glass that have become stretched by the slow flow of solid glass. Ice does that too. Glacial flow due to internal deformation is slow, a rate of maybe inches per day. What happens is ice crystals reorient, ice layers deform, and glacial mass transfers from zones of high pressure to low pressure. This results in some very interesting features in a glacier. Everybody that has dealt with any kind of ice understands basal sliding. The easiest example is ice skating. As you slide over the ice surface, the weight of your body is all on the blade of the skates. This generates an awful lot of pressure. The pressure on the ice results in a phenomenon of pressure melting. The ice melts beneath your ice skate and lubricates the contact between the ice and the metal of your blade. As a result, you glide easily. Compare that to a little kid on double runner blades. The kid almost doesn't weigh anything, and the weight is spread out over two runners on each skate. There's no pressure melting. The little kid goes click, click, clicking along, and of course, if you're skating with them, you are gliding, and they're click, clicking. The result is the parent falls, and the kid laughs. It's great. Pressure melting is one of the reasons ice is so slick. You put weight on it, a car, a boot, or a bicycle, water is generated on the ice surface and slipping occurs. But one of the weird things about ice is that it is slippery even without pressure melting. Anyone who has skated outside in northern winters knows that your skates still slide even down to minus 30 degrees Celsius, which is too cold for pressure melting. You can make ice or snow slippery just by friction. Skiers don't generate enough pressure to melt snow, but they do generate enough friction to make it slick. Basal sliding in a glacier is predominantly the result of the presence of water due to melting throughout the glacier caused by warm air temperatures, combined with pressure melting at the glacier rock contact. A layer of water is generated at the glacier's base, and the glacier literally slides as an entire block. Normally, a glacier will move at a couple of feet per day, but if enough water builds up underneath the glacier, you can get glacial flow rates of over 100 feet per day. That's not anything you have to be afraid of. You can walk faster than 4 feet per hour. Everyone knows that ice is less dense than water, so it floats. But the volume change that occurs during freezing can generate between 25,000 and 114,000 pounds of pressure per square inch. Also, when combined with other substances, such as rock, ice can be fairly strong. Pure ice is not that hard. At 0 degrees, ice has a hardness of 1.5, and at negative 40 degrees, it has a hardness of 4. But with the addition of rock, sand, or dust, ice can generate significant erosional forces and resist fairly substantial impacts. During World War II, the Brits got the idea of building an aircraft carrier out of ice. After all, icebergs are very hard to destroy. It was a top-secret effort that came about as supplies of metal began to run low, and submarines were creating havoc with the British fleet. An engineer named Geoffrey Pike started to do some experiments with ice mixed with sawdust, paper, and other fibers. He eventually settled on a ratio of 14% sawdust to 86% ice. It turned out the product, which he called Pykrete, could withstand artillery. At one point in the project, the design envisioned the largest ship ever built out of ice. An historical marker at Lake Patricia in Canada's Jasper National Park shows where a mock-up of the ship was built nearby. But demand for an aircraft carrier made of ice essentially went away with developing technology as the Allies began using Iceland as a military base. Pykrete still reappears now and then in cold climate construction practices, though mostly only as a curiosity. Ice with rock and sand frozen to its base takes on similar characteristics to Pykrete. Such ice mixtures are hard to deform, so they can generate large amounts of pressure at the interface between basal debris and bedrock. This is why ice combined with sand or rock can generate enough force to abrade bedrock while clean ice cannot. The process of abrasion is the fundamental process of glacial erosion. Abrasion is the process of grinding the underlying bedrock. It's a lot like the process of sanding a piece of wood. In the case of sandpaper, the paper needs grit. In the case of a glacier, the abrasion of bedrock requires debris and sand frozen to the base of the glacier. Of course, you also need motion. With a glacier, the motion is basal sliding. The third important thing is pressure. If there isn't enough pressure, glaciers don't abrade. There are other things that matter. You need a continuous supply of basal debris, and you need rock types that abrade effectively. For example, a quartzite will be more abrasive than a limestone. Glacial abrasion produces glacial flour. Glacial flour is small particles of clay to silt-sized particles, which are generated underneath the glacier. In fact, glacial flour becomes the signature feature at the margin of glaciers. The milky white color of rivers that form from glacial meltwater is due to the high sediment load of that fine-grained particle. And that beautiful turquoise green color that shows up in lakes near glaciers, that's due to glacial flour as well. It's fine-grained and it remains suspended in the water column, where it refracts light in that green wavelength. But watch out. It's always a tactical error to walk up to a glacier without being careful. False steps can put you knee-deep in glacial debris that is a soupy mix of water, rock, and glacial flour. In addition to abrasion, there are other ways that glaciers erode. The glacier can freeze on to subglacial material and pluck it. Individual boulders in glaciers can fracture the bedrock, and the pieces are incorporated into basal ice. Or pre-existing rock fractures can be exploited when meltwater refreezes inside them, fracturing them even further. Glacial erosion features occur on scales from the microscopic all the way up to the scale of an entire landscape. Scratches, called striations, and the presence of polished rocks indicate erosion beneath the glacier. There are amazing glacial grooves on Kelleys Island in Ohio that are just mesmerizing examples of glacial erosion. 3 other impressive glacial landforms are glaciated valleys with high valley walls, like in Yosemite National Park. Amphitheater-shaped depressions called cirques that are found in the highest mountains that frequently contain lakes called tarns. And the spectacular horns, like the Matterhorn, which is the result from cirque formation on 3 sides of the mountain. Glacial deposition can be closely related to erosion. We talked about the pressure of the glacier that is exerted during abrasion. But what if the pressure increases just a little bit? If there's too much pressure, there will be too much friction, and the basal material won't move. In fact, the increased pressure results in the basal material getting deposited. And there are other ways a glacier deposits material. A glacier can dump material that is on the ice surface at its margin, or glaciers can bulldoze material. The result of these depositional processes is a sediment called till. Till contains a mixture of multiple size particles and multiple rock types, including house-sized boulders, all of which are samples from the bedrock that the glacier has ridden over and eroded. Glaciers have the ability to transport individual stones hundreds of miles. The result is rocks that have nothing to do with the local geology. These are called erratics. In the movie The Shawshank Redemption, geology enters into the storyline several times. The lead character is interested in practical geology. There's a rock hammer, also a search for rock types that he can carve into chess pieces. There's also an understanding of deep time and the uniqueness of erratics. At one point, the lead character, the geologist, writes a letter to a friend telling him to go to a farm field that is surrounded by a stone fence. His instructions are to look at the stone fence near a tree for rock that has no earthly business in a main hayfield. It's an erratic, and everyone watching the movie can see that the lithology of the rock is very different from the rest of the rocks in the fence. It's a great landmark, and it leads to an important discovery. Now, when particles are transported by wind or by running water, eddies and turbulence will create multiple flow directions that transport particles in multiple directions. But a glacier will transport particles in a direction that is essentially parallel to glacial flow. Many times, this is a straight line. This linear pattern is called laminar flow, and it's relevant for locating economically important materials. The goal in such cases is to use trace amounts of diamonds or gold found in glacial deposits and then trace the sediment back to an economically significant source of that same material. One ambitious, not yet successful variation of this idea was conducted in Sweden using dogs who were trained to smell sulfides that often accompany economically significant minerals. It's a great idea. Glacial sediments are also deposited by wind blowing glacial flour from a recently deglaciated area. The wind-blown material associated with glaciers is called loess. It's derived from a German word. The Brits just refer to loess as dust. Loess is characterized by its fine grains of silt-sized particles. But also unique for a wind-blown sediment, loess shows up in thick accumulations that can form relatively high cliffs. During the last glaciation, loess was deposited well down the Mississippi Valley, where it played an important role in the Civil War history of the Mississippi Valley. The Battle of Vicksburg happened where and how it did in part because of the Loess Bluffs near Vicksburg, Mississippi, an important river town. Pemberton's Confederate soldiers could easily entrench into the loose, fine-grained loess, and they encircled the city with well-designed trenches that were structurally sound. Additionally, the bluffs that Grant's Union soldiers had to climb would become slippery because of the fine-grained nature of the loess. The entrenchments withstood General Grant's first two charges. Recognizing the quality of the defensive position, Grant decided to lay siege to Vicksburg, an ordeal that lasted over 40 days. While Grant's armies could receive supplies and reinforcements transported down the Mississippi, Pemberton's army grew hungry. Eventually, Pemberton surrendered. Landforms that are created by glacial deposition have an interesting trait. Glacial deposition often results in inverse topography, where holes become hills. For example, meltwater tunnels that form underneath glaciers frequently fill with meltwater sediments. When they formed, these tunnels were insignificant compared to the thickness of the glacier. The tunnels were frequently less than tens of feet high, while the glaciers were thousands of feet high. But when the glaciers are gone, the sand and gravel that filled those tunnels remain as a ridge on a flat landscape. These ridges are called eskers. That's inverse topography. The filled tunnels become ridges. Similarly, vertical holes called moulins form on the surface of a glacier, where water frequently drains in and debris will collect. Moulins are relatively small compared to the size of the glacier they form on. But when the glacier disappears, you're left with the debris that filled the moulin, which stands as a hill. Yet another interesting example of inverse topography is formed by blocks of ice collapsed off the edge of a glacier as the margin retreats. As a glacier melts, chunks of ice break off. Some can be the size of large buildings. As the retreating glacier deposits more material, the ice chunk can be buried. Because of the insulating effect of the overlying debris, the residual ice block can last a long time before it finally does melt, forming a depression. Frequently, where there was once a large ice block, the resulting feature is a hole filled with water. Many of the 10,000 lakes in my home state of Minnesota formed as ice block lakes. One way to have a glacial experience, if you ever get the chance, is to visit a gravel pit with glacial sediments. They're found in most counties of states that have been glaciated. I had a professor that used to say that there was a thesis in every gravel pit. They are a geologic nirvana. Some glacial gravel pits have sediments that represent almost every type of geologic process: rivers, wind, mudslides, glacial tectonics, and lakes. Normally, you look at a gravel exposure and expect to see sedimentary beds that are flat-lying, but frequently glacial sediments are deformed in every manner possible, and each deformed bed is made of different material. Complicated exposures indicate the diversity of processes that occur at the edge of a glacier. Beyond visiting places where glaciers previously moved around, I would encourage you to go visit a glacier for yourself. They are spectacular and beautiful in their own way. But you do have to take care. They can be dangerous. You should never go on a glacier for the first time without a guide. You can sign on to glacier tours of the Athabasca Glacier in Canada's Jasper National Park, the Matanuska Glacier outside of Anchorage, Alaska, and even helicopter onto the Columbia Glacier in Prince William Sound, Alaska. The reason you need a guide is because glaciers have crevasses. Crevasses are cracks that form as the glacier flows faster than the ice can deform, so it splits. Crevasses can sometimes be bridged over by snowfall and difficult to recognize. Falling in them is a very serious issue. You should never jump over a crevasse. If it is too big to step over, don't try to cross it. Also, never walk through fresh snow on a glacier. You don't know what is underneath the snow. There could be a crevasse. With proper guidance, you can enjoy a spectacular experience. The unique sights, otherworldly sounds of ice in motion, and the exhilaration of a cold region all make glaciers a remarkable experience. There's another reason I'm encouraging you to visit a glacier. The ones in the United States and the southern Canadian Rockies are melting at a fairly rapid rate. Especially in the US, you should go see glaciers while they're still here.